All right. Okay, shall I start? 1 minute ahead of time. That's the first time a workshop is ahead of schedule. Okay, so thank you, Luigi. Thank you, Alex. Thank you, Andre, and all the organizers of the workshop. I'm going to talk about a work that we're actually going to present also today at ICRA, and a couple of other things we've been doing at TRI on pedestrian intent prediction. And this is a joint collaboration with Stanford. All right. So this is always my first slide in all of my talks for the past, I would say, almost 3 years now. This is the number of traffic fatalities per year in the world, so 1.35 million. This is kind of a crazy number if you think about it. I think it almost took like another type of pandemic to potentially lower that number a bit. But the real question is why? Why is that number so high? And if it was easy, if it was just an engineering problem, then we would all be war criminals, because that's just the scale of a war in terms of number of deaths. So it's a very, very difficult problem to solve. And in the US alone, there's like 37,000 deaths per year. But if you look at the number of miles traveled, it's like 3 trillion miles traveled. So it's like 1 death every 100 million miles. So it's a very difficult problem, and that's why basically Toyota created us, Toyota Research Institute, 4 years ago to really work on the research challenges that are basically blocking us, preventing humanity from lowering that number. So we've been doing a lot of research, and I'm not going to talk about most of it. You can find everything online because there's no such thing as science behind closed doors. So we're doing everything in the open. But I'm going to talk about one particular instance because that's the topic of this workshop, which is about pedestrians. So here's an example of a sequence, and I'm going to replay it because it's pretty fast. Please pay attention to the pedestrian crossing, and that's one of our TRI cars there. This is a pedestrian move. I don't know if you saw this very quick little hand gesture. So this is just to tell you an example of, you can model the trajectory really well. You can even model the rules of the road, the right of way and everything, or free space. There's always going to be a long tail, an edge case that's going to beat you. And here, for instance, this is very small hand gesture, very few pixels moving very quickly that basically tell you, hey, here the safe thing to do is actually to go forward, or what the human would do is to go forward, right? And just avoid conservatism, because like if you're conservative, you're not moving, and then nobody wants to use your autonomous car. So this is a very hard problem, and it is not just about the trajectory. It is not just about the maps. It is about many, many different subtle factors that vary depending on the particular situation. And so what this calls for, tackling this problem of really understanding what pedestrians are doing, this calls for like a holistic and subtle reasoning across the board, right? And so here, what we've been working on in this particular paper, then it's been, well, one of the key things we would like to understand is the intent to cross or not, right? And so that's like one of the basic, fundamental, and safety critical interactions between a pedestrian and a self-driving car. And so here you see an example of a scene from one of our driving logs. So we have a fleet of level 4 prototypes. They're not really level 4, but we're trying to make them better and better at this. And they go around cities, and we test them, we acquire data, etc. So this is an example of a real world scene. And you see here classical jaywalker, but it's totally reasonable that the person would cross there. And so we do not expect the car to fill in the gap and just bump into the pedestrian. So how do we go about like having like reproducing this kind of natural behavior? Like every driver that is not drunk would actually just behave this way. So how do we make a machine do that? So first of all, obviously, you detect the pedestrian, right? So you need to know there's something there. You need to know that there's a pedestrian. So robust perception is the cornerstone of everything we're doing. There's nothing you can do if you don't have robust perception. But as Dario was showing just before, pedestrian detection is actually already quite good. So now it's not enough, obviously, to detect that there's a pedestrian, right? Because that pedestrian might just be waiting on the side of the road and not moving. And so there's a bunch of things we want to know. Again, I think Dario showed like a really explicit model with lots of attributes that if you know about this, if you've labeled a lot of the data about this, this is great, because then you can really apply theory of mind and say, like, really think about, like, is he looking at the car? Is he leaning forward? And does he want to cross? And then eventually from that, you can reason, right? You can really say, oh, I think I should stop because the pedestrian will want to cross because, right? So you can really do a causal modeling. But this is very difficult to So at a high level, first, what we do is, we basically just have this sensor stream, and we're going to first run scene understanding algorithms. So we use like panoptic segmentation. So we have a couple of recent works where we push the boundaries on panoptic segmentation, which is a really nice, fully like holistic scene parsing algorithm. But really what we care about here is a few categories and a few areas, like crosswalk areas, like traffic signs, traffic lights, cars, pedestrians. So we just parse the scene according to a deep net, which can make models, right? So again, like if you reason explicitly, there's no such thing as a symbol there, right? It's just predictions. And then you're going to build that graph, that scene graph on top of that, right? And here we build a graph that's centered around the pedestrian. And so the pedestrian is the center graph. It's a star graph, right? Where the pedestrian is connected to all the other elements in the scene, but they are not connected to each other. So it's not like a fully connected graph. We also connect the pedestrian node to each other in time, right? And we do not connect all the nodes with each other. So again, it's not like a fully connected spatiotemporal graph, right? We connect just the pedestrian nodes to the future pedestrian nodes, or like the present to the past. And I'll explain the reason for this later on. And so now what we have is we basically have a spatiotemporal graph, which is sparsely connected in time, and star connection in space. And from that, we want to analyze that graph, and by analyze the graph, I mean analyze the nodes, so which is, you know, the pedestrian looks like, where the pedestrian is with respect to the crosswalk, etc. And we want to analyze the edges, the connections, and how these interactions evolve over time. And from that analysis, we're building basically a predictor that will predict the future crossing probability at a given time horizon. So let's say 1 second in the future, 2 seconds in the future, up to 3 seconds into the future. So more specifically, I said, like, we're talking a lot about analyzing this graph and prediction, but I haven't explained exactly how we do it. So again, as you have a sequence of input frames, and our model first conducts the scene parsing. So as I mentioned, you can use panoptic segmentation there, or like just your favorite combination, efficient combination of instant segmentation, semantic segmentation, or 2D, 3D detection. Then you define this pedestrian-centric graph. So as I mentioned, let me try to show my pointer. You have the pedestrian here, a summary node, which basically represents the overall context, and then the different cars here that you see in the scene. And then it's connected in space, but it's also connected in time, as I mentioned. And this connection in time between the pedestrians, we also do a connection between the context nodes. So it's not critical, but this helps a bit. You can then basically use the framework of graph convolution. So graph convolutional neural networks, they basically enable you to update feature representation for the nodes based on the overall graph. And then using this graph convolutions, a few iterations of graph convolutions, we basically update the representation of the pedestrian and the context to be factoring in the full context and the full gamut of interactions. And then what we get is we get these embeddings, and we can then feed the sequence of embeddings into a recurrent network, so a GRU in this case, to basically make the future predictions. So we evaluated on the standard JAAD dataset, joint attention in autonomous driving dataset, which is a dashcam dataset that has been labeled for a variety of pedestrian behavior. So we focus here again on the cross, not cross. And we compare accuracy average over the full future that we predict. So so it's this data set of 30 FPS. So we can do the accuracy over the next 30 predictions, which represents the full predictions over 1 second, or just the prediction exactly 1 second into the future. There's a couple of different methods that we compare to, and we outperformed them all by a significant margin. So first of all, trajectory forecasting. Constant velocity, surprisingly strong baseline. If you're not using constant velocity as a baseline in your trajectory prediction models, you're doing something wrong. Just compared to this, it's surprisingly good. It's better than some state-of-the-art methods. And so we also did some past work presented at WACV, also collaboration with Stanford, on pose forecasting, because pose obviously is such a huge information when it comes to crossing or not crossing. Like if you're tilted towards the edge of the road, obviously it's very strongly correlated with your intent to cross. So we outperformed trajectory forecasting. We outperformed pose forecasting. So not just forecasting trajectory of the pedestrian, but forecasting its locomotion, like it's how it moves. And then also action anticipation. You can just formulate this as an action prediction problem. Is that pedestrian going to do that action in 1 second? So it's really just a classification of the future. And there's a bunch of different networks to do action anticipation or prediction that we also significantly outperform. We did additional experiments in a different setup. So the graph, the spatiotemporal graph that I was mentioning before, is pedestrian-centric. We're wondering if that pedestrian is going to cross. Imagine a scene where you have hundreds of pedestrians. So we are doing testing in Japan, and especially ahead of the Olympics, that has been postponed next year. But you have scenes in Shibuya in Tokyo, which are like hundreds of pedestrians. So if you want to ask that question and run that graph network for each of those pedestrians, or let's say even just the ones in your vicinity that might affect your plan, it's very difficult to make this model fast enough. So another way is to flip the problem on its head and to think about, well, is there someone that's going to cross in front of them? Anyone. And here you build a same thing. You can build a spatiotemporal graph where the graph is now centered on the ego car, right? So it's still star-shaped, but it's really the ego car is the center of this graph. And then obviously you connect it to all the different objects and scene elements, the context, and you connect it through time. Same way as before, you just swap the roles. The pedestrian becomes now just an agent, and then the ego car becomes the center of the graph. And here, for this problem, so there's no real method that does that, right? Because all the other methods are centered on the pedestrian and they're forecasting a trajectory. Our approach, we can really ask this question of like, in this area, red area, is there something that is basically, like we can ask the question about that. Is someone going to cross? One baseline is to not update these embeddings based on graph convolutions. It's just take the embeddings, like the representations we have for these different elements, and just make the prediction using the RNN on it. This is the concat baseline. We vastly outperform this baseline. So what this basically means is that updating the embeddings to make them like acutely aware of everything that's happening around them and the dynamic interactions with all the scene elements is actually making a huge difference for this problem. We also studied the question of longer term prediction. And so here the idea is to predict, you have 30 frames of context and you want to predict for the next 30 frames, 60 frames, 90 frames, so up to 3 seconds in the future. We can do that as expected. It's actually becoming harder and harder over time. We did additional experiments. So this paper was accepted at ICRA and RAL, so it was nice. We had 2 extra pages, so we could add a lot more experiments. So I encourage you to look at the paper for details. But we look at accuracy and confidence. We're outputting probabilities, so uncalibrated probabilities. So we should make some improvements based on that. But basically, you see that the further you predict into the future, again, same thing, the accuracy decreases, the confidence decrease. One highlight there is that if you want to predict further into the future, like let's say 3 seconds into the future, you should not roll forward a model that's been trained for 1 second and just continue rolling it forward. You should train a model directly for predicting with the time horizon you care about. So just Occam's razor, like train for what you want to predict. Some qualitative results. So here's on the JAAD dataset. So in green is when we start to predict. So blue is the observation. Red is we're predicting in the future that it will not cross, and green that it will cross. So you can see here the person's on the side. They're now predicted that they're going to cross 1 second into the future. Right. I'm going to skip in the interest of time. One thing that I wanted to mention is that in this paper, we kind of like realized that although there's a lot of really cool data sets for intent prediction, there's not really many. And they're kind of small. And one of the other things that we know is obviously we're arguing about context here, but context also means the sensory context, right? So the field of view. So we created a new data set outside of the TRI fleet and that we did jointly with Stanford. It's called STIP, Stanford-TRI Intent Prediction data set, which contains the full 180 degrees field of view in the front of the car. And what you'll see is that in big cities and big roads like San Francisco, as you see here, like prediction requires understanding of what's happening at the periphery. And so we labeled the data set and all the frames in synchronization to be able to basically do intent prediction with the full like 180 degrees field of view from these 3 cameras. It's pretty big. It has more than a million annotated frames, 3.5 million pedestrian instances. And again, these 3 cameras, and it was collected in 5 dense US cities. One of the things we have the results on this data set, and one of the things that we could do is we could see if really using the additional context frames, the left and the right frames in addition to the front frame, was it helping as we expected? So yes, it does, and in some cases it improves a lot. Interestingly, in this 4-second case, we try to predict really far into the future with a really long context window. You can actually perform slightly worse, and I guess that's because there's just too much information to digest and confuse as a network. So to conclude, really pedestrian intent prediction, it's an ill-formed problem, right? It's ill-posed problem because intents are non-observable, right? They are latent, they're inside your head. So it's really all about modeling the dynamic context. It's not about how well you represent pedestrian, it's how well you represent the whole scene and the interactions within the scene. And for that, really, spatiotemporal graph neural networks actually rock. They work really, really well. And again, prediction is like not solved. As Dario was saying, prediction is hard, especially about 3 seconds in the future. It's still very, very hard. So you see some examples, 1 second in the future is not enough to react. It's not enough to really make that information useful. So we need to expand the horizon. Just a bunch of additional references that we used. So if you want to forecast the future of the pose to do more complex reasoning, like the example of the gesture that I was talking about at the beginning, we have some work on pose forecasting. We also use a lot, it's all 3D. So all the reasoning, everything we do in the world in autonomous driving is obviously in 3D. So even though we deal with pixels, we care about the 3D structure. So we have a CPR oral that we're going to present in 2 weeks on depth estimation and pose estimation that we use for this work. Another important part that we could build upon is panoptic segmentation. So we have running, like in real time, very sophisticated models for scene understanding, scene parsing. So this panoptic segmentation, which we'll also present as a CPR oral in 2 weeks. And then finally, one big thing is simulation. We have also a new work on just predicting the trajectory and predicting intents in the form of like future endpoints. It's also collaboration with Berkeley and Stanford. And finally, simulation is also key. And you can really try to make predictions about safety critical events when you when you leverage simulation properly, but this is still very, very hard to simulate pedestrians. Data set, code, everything will be available or is already available at this address, at this website. And I would like to thank my collaborators at Stanford, and especially the Stanford Vision Lab, and Juan Carlos, Isan, Bing, Zhangye, Abhijit, and my colleague Juan at TRI for this awesome and important work. Thank you.
Great. Thanks, Adrien. Very nice talk. So we have here a couple of questions. So we do have a couple of minutes for those questions. So maybe we can start from the first one. So how do you choose, how do you choose the nodes? Is it always the same type of node, so you can change dynamically? And I think it's also related to the next one. So essentially, how does this model scale with multiple pedestrians? Or do you consider also group behaviors and so on?
This is very good questions. So to the first part, we have a fixed set of categories. So again, because we use the sim parsing algorithm, we basically just say we care about these agents. So the agents we care about is basically the pedestrians, the car, like the vehicles, the traffic lights, and some like the road surfaces, like the crosswalks. So we do assume that we basically have a bunch of symbols of categories that we care about, and those are the nodes, and those are the types of the nodes that we model. Obviously, as I was mentioning, there's an argmax lying somewhere, right? Like when you say a pedestrian, it's actually not a pedestrian. It's a probability that you decided to discretize into, all right, argmax of the probability, then it's a pedestrian. So together, actually, Marco that you've heard about before, and Boris, we're looking into ideas to relax that assumption that you need to basically know precisely the type of the object and basically make it fully probabilistic. All the states should be distributional. It should not be, you should like put your argmax as late as you can, basically, if you want to be probabilistic. So that's what we're trying to do. And the second question on, so then how does it scale? Obviously, to very, very complex scenes, the graph is very, it becomes unwieldy. But I want to highlight two things. One is that the graph is sparsely connected. So when you ask the question about specific pedestrian, you want to know that the specific pedestrian is going to cross or not. Because let's say, for instance, it's the closest one. Then the graph is still like connected in terms of a star structure and then sparsely connected in time. That's enough to propagate basically the information in time by connecting through the pedestrian. You can further reduce it to very dense environment. You can further reduce it to nearest neighbors. You can basically ignore some nodes. So disconnect them from the graph, and then they're not used in the computation in the graph convolutions. And then we also have the flipped on its head version of the problem, which is the graph centered on a region in space. And that same thing can scale pretty well. And you can all do the same tricks that I mentioned using nearest neighbors, etc.
Mm-hmm. Okay. For the sake of the time, I think we should go on with the next speaker. But we really would like to thank you, Adrien, for the amazing talk. Thank you.
Thank you so much.